It's an electromechanical system for me. Okay. It's an electromechanical opto and whatever you can bring out any discipline of the engineering, you can insert that. I just wanted to learn my engineering and take the course going ahead. And somehow, because this open arm welcome by the space industry, I was given this opportunity to join Indian Space Research Organization. As a ISRO scientist, they allow you to see multiple systems. They allow you to be part of multiple different domains of technology.
Why would I use satellite imagery? Why can't I just fly a drone or maybe take a... Hello and welcome to today's podcast. In this episode of the podcast, we'll be discussing on Earth observation ecosystem, the satellite imageries, their application, what are the parameters apart from the resolution that you should take note before buying your satellite imagery data. And to discuss this with me, we have Mr. Ankur Singhai, a senior space systems engineer at KaleidEO. He is an ex-ISRO scientist. Ankur has completed his bachelor's in electronics from NIT Bhopal, and post his bachelor's he pursued master's in VLSI technologies from IIT Delhi. Welcome on board, Ankur.
Thanks a lot, Yamin, for this brief introduction. But first of all, thanks a lot for this. And I would say that space is a sector where there is no discrimination at all. So people from each and every stream of the education, they are somehow fitted into this ecosystem, and that's where I see myself also getting into this. So I basically started as an electronics engineer, and to be very frank, I never thought that I'll be joining this industry. So many people typically have this aspiration that once I grow up, I want to become an astronaut, or I want to become a something person contributing towards rocketry, satellites. But my goals were very simple. I just wanted to learn my engineering and take the course going ahead. And somehow, because this open arm welcome by the space industry, I was given this opportunity to join Indian Space Research Organization. And again, because of the same, as a ISRO scientist, they allow you to see multiple systems. They allow you to be part of multiple different domains of technology. And that is what prompted me to look ahead of what I was doing. And I joined KaleidEO Space Systems, where we are building optical payloads of different classes as a senior space satellite systems engineer.
A good insight. I mean, an engineer is supposed to, do engineering. I mean, and you kind of grew into that role as you moved ahead in your career. As for me, I was like initially very enthusiastic about the space career and all.
Nice.
I pursued aerospace engineering. I knew what I wanted to do, and then I started to work in the space industry as well. But yeah, I mean, lovely to have you here, Ankur. Let's dive head first into our today's podcast discussion. As we were discussing, there are different kind of Earth observation satellites available to us. Broadly, if I have to categorize, I'll categorize it into three parts: multi, hyper, and SAR. What are these three different kind of satellites? What are their applications? If I have to use the data, when to use what data? Where does it fit right in? And why would I use satellite imagery? Why can't I just fly a drone, or maybe take a helicopter or a UAV which stays for a longer duration of time? I know like endurance is going to be an issue, but if we do it, why satellite imagery first? Different kinds of satellite imagery, what are their applications? Please.
So there are multiple questions that you have posted here. So
Sorry about that.
So to start with that, I think the very preliminary question is, why do you want in terms of a remote sensing environment, why do you want to go for a satellite imagery when you have such other platforms available which
Yes.
you can fly at your will, right? Satellites is something that you have to plan in advance. You have to make a satellite, you have to book a seat in the launch vehicle, and you have to fly. So there's a lot of mission planning and long-term planning needed for this.
It's a capital intensive
and it's a
industry.
capital
I mean,
industry,
yeah.
I mean, so, and the failure chances are too high. Still, the industry is not mature to that level where you can say that very confidently that if I'm launching a satellite, it will survive in space for next 5 years. So,
Yeah.
but still people are going for that, right? So there is definitely some thrust which is
Driving this.
driving this technology to move towards the space-based application, right?
Yeah. Why would I
If-
use
if-
satellite
if-
imagery? Why not I use a UAV imagery or a drone imagery?
Correct. So when you say when you see a satellite image, you can get a bird's eye view of a wider area at a time, in comparison to if you use a UAV or any other vehicle.
Okay.
It can be a aeroplane-based surveillance system, or it can be drones or anything.
Yeah.
The area that they cover at a time is not that massive in comparison to what satellite can give you in a single picture from a very high altitude. So that's the very first advantage of it. Second is as the technology is maturing, you can use more and more smart sensors, build smarter platforms. You can build solutions with onboard processing. So satellite technology is maturing, so it's allowing you to use more and more power. It is allowing you to use more and more space on your platform.
Is the industry currently using, as you said, right, you can do onboard processing of the images. So is the industry currently employing AI models to detect it on board and not have to downlink and then get the insights? Is it the trend?
Definitely. This is the trend which we are moving to. So EO industry is undergoing a tectonic shift since the inception of highly reliable electronic systems which can be sent onto the satellite platform. Now we are seeing more and more COTS components which are behaving and surviving throughout the lifetime of your satellite. So because of these engineering advancements, you are able to bring down the cost of your platform and put more and more complex system on your platform for the same cost, and do more and more processing and directly deliver the relevant information to the end user.
Let's start from the beginning. Why satellite imagery?
See, satellite imagery allows you to monitor a wider area at a time. So there can be applications where you need to measure small areas. So there you can go for UAV based or any other aerial survey based systems. But when you want to do it at a larger scale for a larger period of time, then there the economies of scale play a factor, and satellite imagery becomes cheaper over there.
Like I was reading up a bit before this episode. So broadly 3 categories in the Earth observation sector, which I have set. Like, so if I missed anything, feel free to point it out. One is multispectral, hyperspectral, and SAR-based imaging. What are these 3 different kind of imaging? When to use and what?
So typically, I mean, these are broadly categorized into an active imaging and a passive imaging setup.
Yeah.
So active imaging is where you irradiate the source, you send a particular wavelength from the source, and you receive on the same transmitter which is sitting near the source. So
Radar based kind of.
so it's a radar based, where the way you used to detect the position of the aircrafts during the World War. So it's the same.
We still
technology.
do, right?
We still do. Yeah. So it was actually borrowed from that era, this technology. Passive imaging is where a stellar object like for us the sun is illuminating certain section of the earth, and the light is getting reflected from those objects and it is detected at the sensor.
Okay.
So it's not the direct object that is sending the light, it's the reflected light from another source. So this is known as a passive imaging.
So except for radar, most of the satellites or payload would come under passive imaging, right?
Mostly, yes.
Yeah, I mean.
That's a broad category, and
Right.
there are other kinds of detectors as well. So you mentioned about multispectral, hyperspectral.
Yeah.
So multispectral is something that you see that you can see from your eyes and to the spectrum.
It feels like how it feels to us. So the imagery will also.
Correct. So in multispectrum, basically bands are quite big. Spectral band definition is quite big. So
Okay.
if you see 100, 200 nanometers is the band definition for each spectral band. Whereas for
100, 200 nanometers.
100 nanometers के आसपास होता है ना, pan band is
Pan is 100, but I mean the total, if you scan, right, so 450 to 900.
No, so that is entire
that will be
band.
like 400.
So you break into suitable bands.
So the total bandwidth is about 400 to 500 nanometers, and then you divide it into
correct
big chunks. You have multispectral.
So multispectral is something starts from 400 nanometers to around 900 nanometers of the spectral band, and there you will divide the entire 400 to 500 nanometers band into some specific frequency bands of your interest. So it can range from 550 nanometers to as good as 100 nanometers, 150 nanometers, and based on that you designate that this band corresponds to my red color, green color, and red edge, near IR, VNIR, all those things.
These are fixed, right? For red is like you know the wavelength.
So this is how the visible spectrum and the multispectral band is characterized.
Okay.
Whereas for hyperspectral, what you do is you have the entire 400 to 900 nanometers band. You break it down into very small bandwidths of 5 to 10 nanometers. So effectively, you have hundreds of bands within the same overall spectra, and then you capture the information in very, very small spectral bands. So the advantage here is that the spectral information that is necessary for mineral classification, for interspecies classification of the different objects, that's where
is the principle. So I got the overall principle, I think, an overlook of it, that you have a total from in the EM spectrum, your visible and near infrared, you have like 400 to 900. If you divided it into bands like RGB, red edge, near infrared, these are your multispectral bands. Then if you divide the similar, the visible bands into 100 or maybe 200 different kinds of band, right? Chop it up. That will be your hyperspectral. But these both are done in the visible ranges.
it may not be true. For hyperspectral, the range can be even bigger. But the idea is to capture the spectral information with very small bandwidths.
So, can you just like for example, let's say I'm not doing all these three kinds of imaging. I'm doing thermal imaging.
Right.
Right. So the thermal will be, it will be in a different EM spectrum, right? So you will not be using the sensor what you're using for these three satellites we were discussing.
So there you will have to use the infrared region of your band. And
how do you decide like how many number of bands you want to split this total? Let's say your infrared domain lies from X nanometer to Y nanometers, right? How would you say like, okay, I'll divide this into 6 bands or 100 bands. So since you have like a lot of options, what are the factors that drive your?
So it basically depends on what you want to measure.
Okay.
What is it that you are trying to find? समंदर में मोती ढूंढने जैसा है. So the specific thing that you're looking for, each and those things have a specific spectral characteristics, which you will be able to figure out only when you
like in chemistry we do spectroscopy, so you kind of get the sodium in that particular band, and that's the signature.
Because everything, all the materials is basically linked to your conduction band, valence band theories. So from that band definition, you will come to know that which material is emitting light of which wavelength corresponding to their band structure. So that is why for different materials with their different
spectral signatures, right?
Material configuration, the spectral signatures will be different.
Yes, yes.
So that's how you decide that what you want to measure, and ultimately it's a business, right? What you want to do. So
okay. Yeah. Okay. Let's delve a little deeper into the multispectral side of things.
Right.
Yeah. So I mean, you go to any kind of platform which sells satellite imagery. The resolution is the buzzword in the market. I have a 0.3 meter resolution. I have a 60 centimeter resolution, and so is it because you see it so frequently that you feel that it's the basic driving force behind the sales of satellite imagery data? Is it true? Like, what are the other parameters, or let me put it in a way, right? That can it happen that you get better insights from a 70 centimeter data then compared to a 50 centimeter data?
So, yeah, I mean,
I
that's
think is it okay? Is it clear? Like what I'm trying to ask here, like
yeah,
what I'm trying to
you're
get.
super clear, Yamin. And I think that's a very relevant question to ask in the current ongoing scenario as well. People are just scaling their imagery to lower and lower, to higher and higher resolutions.
Now we have the VVHR, very high
Very, very high
resolution.
resolution.
Yes.
I mean, yeah.
I think it's less than 0.3, right? The VVHR.
Yes, people are making 10 centimeter, 20 centimeter resolution payloads as well now. Right?
Okay.
So,
But just a second. So the 10 centimeter, I think that's the physics limit, right? Your atmosphere moves, there's scintillation.
with
other
respect to
stuff.
the atmospheric seeing limits and diffraction limited,
This 10 centimeter, like you cannot go less than 10
there
centimeter.
are software ways to go below that as well. That's where when the physical limitation of the hardware comes, that's where your software techniques kick in, and they help you to improve.
Okay,
the
so
result.
it happens in post processing.
It happens in the
native
post-processing.
image you cannot capture less than 10 centimeters.
So whatever the data that you see commercially available,
Uh-huh.
they never tell you that that has been captured at the raw hardware level or it's a post-processed. They will simply say that it's a 70 centimeter resolution data that you have to buy in this panchromatic band, and for multispectral it is this, and there are techniques to sharpen it to those panchromatic levels. So this is how the data is being sold in the current
So
business.
when-
But what I want to come back to is
Yeah.
that people see that resolution is a panacea for all their problems, right? It's a one-shot solution, but it is not like that. I mean, resolution cannot be the only thing uh, that is pushing you to get better business
But
insights,
it is
right?
the lion's share of your differentiator in the market, right?
It is similar to how the VLSI technology proceeded. People started moving from 180 nanometers to 90 nanometers to coming down to up to now 5 nanometers, 3 nanometers chips which
It's
are
just
there.
mind-boggling. I've
Right,
seen
so-
those videos where they kind of zoom into
Yeah, so
it
that's
and
what I'm
it's
telling.
just
So it's just I mean, scaling to lower features, or you're saying that I'm able to measure two features which are of this feature size, is not the only criteria for your final business goal. Okay.
So,
So typically when people say that resolution, right?
yeah.
So I am coming to you what you were trying to come to, right? So we talk a lot about spatial resolution, right?
Yes.
Where what's the capability of my eyes or my camera to see if the two objects are very close to each other. So what is the minimum distance between them so that I can try to.
Let's take our railway track. It's
It's the
0.8
railway
meter
track.
gauge, so you should be able
Correct.
to differentiate, right?
So that is the one kind of a resolution that we tend to focus on, or which the current industry is trying to focus on. So there are other kinds of resolutions as well.
Okay.
So another resolution is the temporal resolution, which basically tells you that if you are imaging over a particular feature, then how frequently can you come over the same feature again and again and take the images. Okay, for example, your geosatellites. You have a geostationary satellite looking at a particular area of the Earth, and it keeps moving with Earth because it has a time period equal to the revolution.
So is the temporal resolution same as revisit time? Like if I improve my revisit time, I get better temporal resolution?
Correct. So if
Because why I'm asking is this, because I thought that temporal resolution is usually when you take a satellite imagery, if you have a 15 or 20 kilometer swath, right? You kind of integrate these strips of images, and so you know that the first strip is at some, let's say, 1st of July 2025. The second strip is at 2nd July. So when you build a total scene out of it, so is that the temporal resolution or the revisit time? Like
revisit comes into the picture because your satellite is moving over different areas, right?
Yeah.
Suppose if you are able to bring your satellite, this is, I think you're relating more to the low Earth orbit satellite constellation, right?
yeah, right now I'm just discussing the low
Correct.
Earth observation SSO satellites.
Correct.
I mean SSO we can see
that we can debate,
yeah,
but it's
that
a
we
low
can
Earth
say.
orbit
Yeah, it's
satellite.
a
right?
LEO satellite.
So the temporal resolution is basically defined by how. So revisit also comes from the temporal resolution, right?
Okay.
Suppose if
Yeah.
you have a revisit time of a particular days. That means after X number of days, you will be again coming back to the same object, taking an image over the same area
Okay.
under the similar sun illumination conditions. Because
Yes.
this
is when you're in SSO, similar
is
sun
your
conditions.
SSO.
Otherwise,
But for a geostationary satellite, because you have always keep looking at the same features, right? Same area of interest. That means you always have a information available about that area, and it always depends on how closely you are taking the frames of that particular area.
so Ankur, I mean, my question here is, can we extract more insights or better insights or better analytics from a 70 centimeter multispectral image data product versus a 50 centimeter image data product? So my intention behind asking this question is very simple. Like, is the resolution worth? I mean, is it like, I want to just quantify the hype around it. So if it's possible for me to get a better analytics from a 70 centimeter multispectral image data, then 50 centimeter, I mean, there is something else at play here. So yeah, please.
So there is a lot of buzz around moving to a higher resolutions, achieving more and more resolution.
0.3 has become the norm. I don't know.
Yeah,
I don't know. I've been seeing.
I mean, other than strategic users, who are the persons who are using it, right? So, but there is a race that is going on towards building a better and better resolution satellite. But one thing that we are not looking on the other side of the spectrum is the quality of the image that you are capturing at that particular resolution. Okay.
Okay.
So the qualities are basically defined by the, if I try to point it out, first the radiometric performance of your payload. Okay. So the radiometric performance means what is the SNR, what is the signal to noise ratio that you are achieving in different bands.
Yes.
Below a particular signal to noise ratio, it may be difficult to run your post-processing algorithms and detect those features from that image which you need for the next level of data processing. Okay.
Achha, what's the, just for a reference, right, so that we can peg our conversation to some of the numbers here. SNR of Sentinel-2 at the given top of the atmosphere, is it like, what's the number?
Usually 100:1 is the reference that we take, that if you are achieving a 100:1 SNR.
At the top of the, so if I am designing a satellite, I'll consider the albedo, see the top of the atmosphere,
Correct.
and try to reach almost 100:1.
100:1. So that is what the current state of the art payloads are giving you. Okay. And anything below that, you are kind of going out of the market, because the optics, the electronics, and the manufacturing technology is getting better day by day. So 100:1 is getting a norm that is set in the market now.
Okay.
Other than this, there are other parameters. For example, the quality of your imaging system. For example, if you are using a lens-based system or a mirror-based system, what is the overall distortion that this system is causing you? Is it measurable? Are you able to correct it? Are you able to calibrate it? And how frequently are those parameters changing? Right?
What
in
are
orbit conditions.
So radiometric performance.
For example, there are different kinds of coatings that you use in your optical elements. Okay. Over the time, there is a degradation. For example, if you started with a 99% absorption, a coating which gives you a 99% absorption of a certain wavelength, so that there are no stray light performance getting into your system. And over the time, if that coating quality is getting degraded, which is bound to happen, right? So you will have an impact down.
So the coating degradation, is it because of the atomic oxygen, because of the space weather? What's the major contributing factor to that?
It's basically the atomic oxygen, and in space.
So that yellowing of those.
Correct.
But that is for lenses, right? For the mirrors.
On mirrors also you have a anti-reflecting reflective coating.
That AR coating is
right.
that
So it's an interplay of all the factors.
Yeah.
And so once you launch any mechanical system, they have a tolerances in between, right?
Will you call a payload, like multispectral payload, a mechanical system?
It's an electromechanical system for me. Okay. It's an electromechanical opto and whatever you can bring out any discipline of the engineering, you can insert that. It's a complex system. It's an interplay of multiple domains, multiple disciplines.
Yeah.
And
Indeed it is.
any discipline which is not getting met or is getting violated here will cause an final
Degradation
degradation
of
of
the
your
image,
image.
right,
For
right.
example, your mechanical system. Over the time, if there are stresses which are getting released from your mechanical configuration, or there is a thermoelastic variation due to in-orbit conditions, right? Those things will indirectly impact the optical performance of your payload.
I mean, as a mechanical, I started my journey as a mechanical systems engineer in ISRO. So I'll say that from the mechanics point of view, if you just take care of the inbuilt stress, that really never contributes. What majorly contributes is the thermoelastic distortions, because this is the variation.
Correct.
Because once you are in the zero gravity, it doesn't matter.
So,
Like you can once you're in the, what do you say, in orbit commissioning phase, just do the CalVal and you kind of get it. So if there is no inbuilt stress into the mechanical systems of a satellite, I mean, you're good to go. But TED is what you kind of keep on solving
there is
throughout the lifetime.
solar radiation pressure that constantly acts on it. There's a gravity that is acting. So over a period of 5 years, you need to manage those stresses. And as the current trend goes, right, miniaturization is the new norm, where you are trying to fit more and more things into smaller and smaller packages
Yeah.
to save on your launch cost, right?
Yep.
So that is making this system more complex, and so that is one part. So these all things control the accuracy of your system, okay, which is a important parameter when you take into account the quality of an image, okay.
Okay.
So resolution is a necessary condition, okay.
Can you give me like quantification? Like you were exploring the radiometry. So what are the different parameters? Like let's say if I'm buying a satellite data, right? I'll ask what are the questions that I'm going to ask. What's your resolution of this image data product? What's the SNR? You've touched upon it. What's your MTF? What's your CE90 error in the horizontal and vertical directions? So can we discuss more on these and like link it to like how all of this contributes to a better analytics derived from these images?
Correct. So yes, we can definitely talk about it, and it's good that you mentioned about the CE90 accuracy parameter, which is a very widely used norm these days to quantify whether once you geo-reference your image, how faithfully it is sitting on the base map when you project the image from the sensor frame onto the Earth's projection.
How much off Nadir image you are taking?
Of Nadir, even the Nadir cases imaging, right?
Yeah.
How faithfully are they replicating the pixels are getting replicated on the ground features which you have captured onto the satellite's frame of reference.
Yeah.
Okay. How well you have characterized your entire payload's geometry, okay, and how you beautifully you have understood the different relief corrections, atmospheric corrections, and different series of corrections which are and transformations which are necessary to translate your image, which are captured in space to the Earth's frame of reference, okay, onto the Earth. So there are it's an interplay of many factors. So that is where your accuracy comes into the picture.
So is it actually possible, right, that I'll get better insight from a 0.7 meter data than a 0.5 meter data?
Exactly. So accuracy, MTF, SNR. Okay, these are the driving factors, and the band-to-band registration that you get for which is a very important factor for your multispectral images. That
Can you explain like band-to-band registration for a layman?
okay.
I mean, we are from the same industry, but I mean, it's a term like which is not regularly used as well, like in other kind of Earth observation content that I go through. So yeah.
Correct. So if you see any detector, which is the heart of your camera system. So camera system will
Some
basically...
people call detector only camera. So
So if I speak on a very high level, there are different types of telescopes. It can be refractive, it can be reflective, and end of the day, through all your apertures and everything, the mirror-red lenses, the light has to be converged onto a detector.
Yes.
Which contains the active elements. Usually, nowadays, for the multispectral and hyperspectral, we are having an array kind of a detector, which has multiple elements, equally sized, equally spaced, spread across in a very regular fashion onto your silicon die. Okay, it can be a CCD or it can be a CMOS sensor. Okay, now the
band-to-band registration.
So it can be possible that you use different detectors for different bands, or you can use a single detector with multiple filter bands onto your detector.
Okay.
So when you are and in a satellite environment, the satellite is continuously moving in its orbit. So when you are imaging a particular area, when I say that a particular area, my detector passes over it. Okay. So so different bands are passing in the same pass, but at different times over the same area.
Just let me go through it again. Like
Okay.
different.
So there's a detector.
Yeah, I mean, I get it. Like it's moving. So at different times, I mean, let's say we are imaging the cup, right? So this will be in the red band, this will be in the green band, this will be in the blue band, this will be in whatever
that will not happen simultaneously.
Yes.
So each band is following the subsequent band.
But it will be in like the fractions of a second, like.
Yeah, it's a fractions of second. I mean, not even fractions of seconds. If you take this cup as a 1 kilometer object, okay, and at a 7.5 kilometer per second speed, it will take what 140 milliseconds to pass over it. Okay.
Yeah, 140 milliseconds.
Yeah.
Yeah, I mean.
So just imagine the sheer, and we are talking about a 1 kilometer image, right? Actually,
if your resolution is, let's say, 1 meter, so you cannot.
0.7 meters you're talking about, right? So just imagine the complexity that will be there in terms of making sure that for each band, the pixels of one band and the following bands are falling in line. And once, suppose if there is a linear detector, an array detector which has linear rows.
Okay.
So the column number 1 of your first band, and on the same column, the element which is falling for the other band. Okay. Suppose the band definition is like this: the first band, the second band, third band, fourth band. So if I take one column, so for different bands, I want the object to be imaged at the same column number.
That's a really tough task. I mean, you have your body errors, you have your yaw inaccuracies. It's supposed to move like in at least 2-3 pixels here and there, right?
So that is where the complexity of your system comes in. That how accurately you are able to make sure that for different bands, the feature is captured at the similar locations. So that once you superimpose one band over, so for a particular area, if you superimpose multiple bands at a time, then there is no fringing that is coming. Means the pixels of the same object fall at the same location in different bands once you superimpose over them. Okay.
Okay.
So this
is that?
Yeah, please.
I've seen this term aliasing.
Aliasing, yeah.
So does that happen when you don't have this same image falling in the same column number of the pixel, or is it something else like?
Aliasing is actually dependent on sampling.
Okay. Yeah. So I got it.
So what you are referring to is smear or blur.
So if you scan, like if you sample it below the Nyquist frequency, you'll kind of get aliasing.
Correct.
Yeah,
so
it makes sense.
So there's a term smearing and blurring, right?
Yes.
Yeah. So when you
image a car going whoosh and you'll see that.
Yeah. So the car is moving at a very slow speed with respect to your camera, but the satellite is moving at 7 kilometers per second. Just imagine.
How many that will be in the kmph? I was thinking. So it will be like 7,000.
So in 1 second you will be moving around 7,000 meters. Okay.
1 second. That's pretty.
So that's a sheer speed which you need to compensate for. if you want to achieve. So there are software processing techniques, there are hardware level techniques through which it is manageable to, or the technology that you talked about, TDI technology.
Yes, yes.
That allows you to capture frames over multiple stages in a very short period of time. So
Okay.
that allows you to have this smearing due to a long track motion contained within a very short integration time. So there are software based techniques, hardware based techniques to overcome this.
Okay. So overall, I get like, so from a imaging, how do you image that, like from the hardware level? I see we can categorize it into two parts. One is your geometric performance,
Right.
other is your radiometric performance. Now, these geometric performance can be subdivided into your GST, which is your ground sampling distance. I know there is a term called ground resolution distance as well, and we are going to talk about it. And the other would be the MTF. While in the radiometric side of things, you have how many number of bands that you have, the spectral resolution, how many number of bands that you have, and what's the SNR. Are these the four major factors? Like, and there are different factors which come from the satellite platform itself. Like the CE90 error is basically from how accurate your platform stability is.
So it's dependent on the platform accuracy as well as the ground processing capability. So ground processing capability means how many ground control points over that particular area do you have? And
So this is for calibration, right? If you have more GCPs, you kind
so
of,
if you have more GCPs, you can actually tie down your pixels to those particular points and increase your
now you know
accuracy.
your lat long, so
So yeah, so you can
the flat fielding.
accurately calculate the extent coordinates of your image from the sensor frame onto the ground frame. Okay, so it's an interplay of the post-processing software capabilities as well as the hardware capabilities. Together, that will define your final accuracy of the system. So whatever you mentioned about the platform accuracies, the thermoelastic variation, that will all impact the platform-related impact on the accuracy.
yes, yes.
Right? Your positional accuracy in terms of how precisely the platform is pointing towards the lat long that you have of the area of interest, right? So those things.
Just to give everyone a context, like the accuracies what we are discussing about, I'll just give you a typical number, right? I mean, it can vary here and there, but in yaw, what you are looking for a body rate, I mean, your body rate in yaw will be around 20 arc seconds per second. So just I'll reiterate, like 20 arc second is 1 degree is 60 arc minutes, and your 1 arc minute is 60 arc seconds. And we are discussing that the stability has to be 20 arc second per second. I mean, that should give everyone a context, like how precise these technologies are.
Right, and that is why as the platform engineering is advancing, you have better actuators, better sensors. So the star sensors accuracy these days now it's very close to 3 to 4 arc seconds.
Yeah, 5. I think our, like in ISRO have used. Oh, it's okay.
And there are newer techniques through which you can bring down the accuracy, improve the accuracy of your star tracker.
Yeah, your AOCS.
So there are some filtering techniques through which you can predict it and then bring your platform accuracy close to 2 arc seconds or something, right? So that is why although your actuator is able to give you 2 arc seconds, but whether your platform is capable of maintaining it within that accuracy or not,
Okay.
that is the second factor. That's where the platform engineering kicks in.